Selected properties of liquids. In this lecture, we will discuss several properties of liquids and their relation to intermolecular forces. The 5 properties we will consider are density, viscosity, surface tension, capillary action, and vapor pressure. The density of a material is defined to be the ratio of the mass of the material to the volume of space it takes up, or mathematically, D is equal to m divided by V. Recall that the strength of intermolecular forces determines how closely molecules are held together in space. The stronger the forces, the closer the molecules tend to be held together. To understand the relationship between intermolecular forces and the density, we need to consider both the numerator and the denominator separately. First, let's consider the mass. The mass of the liquid is determined by the sum of the masses of the individual molecules. Since the total mass of the individual molecules does not depend on how close they are in space, we can expect that the mass of the liquid will not be affected by the strength of intermolecular forces. Next, we consider the volume, which is dependent on the intermolecular forces. In a liquid with strong intermolecular forces, the molecules are held closer together than in a liquid with weaker intermolecular forces. As a result, the volume of a liquid with stronger intermolecular forces will be smaller. Returning to the definition of density, we see that as the volume goes down, because it's in the denominator, this causes the density to increase. Let's now consider an example. We're going to list the following liquids in order of increasing density based on the predicted intermolecular forces. The 3 liquids are 4-heptanone, octane, and hexanoic acid. The first step is to determine the predominant intermolecular forces in each of these 3 molecules. We begin with 4-heptanone. The first question we ask is, are there any hydrogens bonded to oxygens, nitrogens, or fluorines? And in the case of 4-heptanone, there are not. Next, we consider if there are any permanent dipoles. Because we have a C double bond O group in the middle of the 4-heptanone molecule, we do indeed have a permanent dipole, and therefore the strongest force in 4-heptanone will be dipole-dipole interactions. Next, we consider octane. Again, we ask, are there any hydrogens bonded to oxygen, nitrogen, or fluorine? And there are not. The second question is, are there any permanent dipoles? Because octane is a long chain of CH3-CH2 groups, we do not expect there to be a permanent dipole. And therefore, the strongest forces present in octane are dispersion forces. Finally, we consider hexanoic acid. Again, we begin by asking, are there any hydrogens bonded to oxygen, nitrogen, or fluorine? In this case, we have an OH group on the end of hexanoic acid, and so the strongest force present is hydrogen bonding. We can now rank the 3 liquids in terms of increasing strength of intermolecular forces. Octane has the weakest, 4-heptanone comes in second, and hexanoic acid has the strongest intermolecular forces. Recalling that density increases as intermolecular forces increase, this tells us that octane should have the lowest density, 4-heptanone should have the next highest density, and hexanoic acid should have the greatest density. When we look at the experimental densities, we see that indeed octane has a value of 0.699 grams per milliliter, 4-heptanone has a value of 0.820 grams per milliliter, and hexanoic acid has a density of 0.921 grams per milliliter. The second property we will consider is the viscosity of a liquid. In the simplest sense, viscosity is the measure of how much resistance a liquid has to flowing. The higher the viscosity of a liquid, the slower it will flow. As a simple example, consider the difference between water, which has a viscosity of 1 millipascal second, and honey, which has a viscosity of 10,000 millipascal seconds. Honey has a much higher viscosity and flows much slower than water. The relationship between intermolecular forces and viscosity is in direct proportionality. As the strength of intermolecular forces increase, the less easily molecules can move around each other. This reduction in the ease of motion causes the flow of the liquid to be reduced, resulting in an increase in viscosity as the intermolecular forces increase. The image to the right is the pitch drop experiment from the University of Queensland. Pitch is a highly viscous liquid which is used to make asphalt for pavement. It is composed of very long, rod-like organic molecules which experience strong intermolecular forces, causing pitch to have a very high viscosity. This pitch was allowed to begin flowing in October of 1930. Over the past 90 years, only 9 drops of pitch have fallen. This makes the viscosity of pitch between 20 and 200 billion times the viscosity of water. Let's consider another example. We're going to list the following liquids in order of decreasing viscosity based on the predicted intermolecular forces. The 3 liquids are ethanol, pentane, and acetone. As before, our first step is to determine the strongest intermolecular forces present in each of these 3 liquids. We will begin with the ethanol. First we ask, are there any hydrogens bonded to oxygen, nitrogen, or fluorine? Since we have an OH group present in ethanol, the strongest intermolecular forces present are hydrogen bonding. Next we consider pentane. Pentane being a long chain of CH3-CH2 groups, we can expect there not to be any hydrogen bonding or dipole moments, and therefore pentane will have dispersion forces as the strongest intermolecular forces. Lastly, we consider acetone. First, we note that there are no hydrogens bonded to oxygen, nitrogen, or to fluorine in acetone. However, because we have a C double bond O group, we know that it has a permanent dipole and therefore has dipole-dipole forces. Now we can rank our 3 liquids. Since we are interested in decreasing viscosity as we rank them, we need to start with the strongest intermolecular forces. Because ethanol has hydrogen bonding, it will have the strongest intermolecular forces. Acetone with dipole-dipole forces will be second, and pentane with only dispersion forces will be the weakest. This means that ethanol will have the greatest viscosity, acetone will come second, and pentane will have the lowest viscosity. When we consider the actual experimental values of viscosity, we see that ethanol has a viscosity of 1.095 millipascal seconds. Acetone has a viscosity of 0.316 millipascal seconds, and pentane has a viscosity of 0.223 millipascal seconds. The next 2 properties of liquids that we will discuss depend on the ratio of 2 related forces in the liquid: cohesive forces and adhesive forces. Cohesion is the tendency for like particles to attract one another and cling together. Cohesion is what holds the droplets of water together in the picture to the right. Adhesion is the tendency for dissimilar particles to attract one another and cling together. Adhesion is what holds the droplets of water to the spider web. Both types of attraction are due to intermolecular forces. However, the more dissimilar 2 substances are, the less they adhere to one another. The next property we will consider is the surface tension of a liquid. Molecules in the interior of a liquid will feel cohesive forces from all neighboring molecules, as demonstrated in the image to the right. As the molecules are positioned roughly equally in all directions, this results in a net balance of forces, which causes these forces to almost completely cancel out. Contrary to this, a molecule at the surface of a liquid does not have other liquid molecules surrounding it in all directions. As a result, there is an unbalanced cohesive force pulling the surface molecules toward the center of the liquid. This causes the surface area to shrink to the smallest possible size, which in 3 dimensions is a sphere. This phenomenon is what causes water to bead up on a freshly waxed car surface. The surface tension of a liquid is the amount of energy required to increase the surface area of the liquid by 1 square meter. The stronger the intermolecular forces in a liquid, the stronger the surface tension, since the cohesive forces inside the liquid are more attractive. The higher the surface tension, the harder it is to deform the spherical surface of a liquid. On the next couple of slides, we will look at drops of 3 different liquids. The more spherical the drops remain, the higher the surface tension and the stronger the intermolecular forces. The 3 liquids we will look at are acetyl-acetone, which possesses dipole-dipole interactions, ethylene glycol, which can hydrogen bond in 6 locations per molecule, and glycerol, which can hydrogen bond in 9 locations per molecule. Each of these liquids has had a small amount of a dye added to them to make them easier to see, but these will not affect the intermolecular forces. First, we notice that the acetyl-acetone drop is not even circular in shape. It is spread out quite a bit when added to the surface. The ethylene glycol has maintained its circular shape largely, but has deformed slightly, whereas the glycerol has a nearly perfect circular shape looking from above. The effect becomes even more pronounced when we look from the side. The acetyl-acetone drop is almost flat on the surface. The ethylene glycol drop is beading up, but nowhere near as spherical as the glycerol drop. From this, we can predict that the acetyl-acetone will have the smallest surface tension, and the glycerol will have the largest surface tension. When we consider the experimental surface tension values, we see that this is indeed the case. Acetyl-acetone has a surface tension of 31.2 millinewtons per meter. Ethylene glycol has a surface tension of 47.7 millinewtons per meter, and glycerol has a surface tension of 64.0 millinewtons per meter. Surface tension can give rise to some very interesting effects. In the image to the right, we see that this Japanese 1 yen coin will float on the surface of the water. The coin, which is completely made of aluminum, does not exert sufficient force to overcome the surface tension of the water. In this image, we see that mercury, which has much stronger intermolecular forces than water, can actually support a 200-gram weight. The next phenomenon that we will consider, known as capillary action, is closely related to surface tension. When an open tube is placed in a beaker of water, the water will rise inside of the tube. The effect is most noticeable when the inside diameter of the tube is very narrow. This effect, known as capillary action, arises because the water molecules, being polar, are attracted to the surface of the glass tubing, which is also polar, through adhesive forces. The attractive adhesion forces stretch the surface of the water, increasing the surface area. The cohesive forces pull the water up the tube to minimize the surface tension. The level will rise until the adhesive forces are balanced by the cohesive forces and the force of gravity. Mercury atoms, which are nonpolar, are not attracted to the glass of the capillary tube. As a result, the surface of the mercury will actually fall in the tube as the cohesive forces predominate. This gives rise to what is known as the meniscus of the liquid. Since adhesive forces between glass and water are stronger than the cohesive forces in water, the liquid surface climbs up the glass, causing a concave meniscus. In mercury, the cohesive forces between the atoms are stronger than the adhesive forces between the mercury and the glass, which causes the liquid to pull away from the glass. This results in a convex meniscus. Capillary action occurs in many areas of everyday life. It is important to phenomena such as the movement of water from the roots to the leaves in plants, the draining of tear fluid in the eye, the movement of groundwater from wet regions to dry regions, the ability for moisture-wicking clothing to draw sweat away from the body, and the operation of fountain pens. The final property of liquids that we will consider is the vapor pressure. Begin by considering an empty flask. We can then introduce a small amount of liquid into the bottom of the flask and seal it up. Initially, at the surface of the liquid, a few molecules will gain enough kinetic energy to escape from the liquid and jump up into the atmosphere above. Early on, the number of molecules escaping is very small. As more molecules enter the atmosphere, a few of them begin to strike the surface of the liquid. These will lose kinetic energy and become stuck in the liquid again. At this point, the number of molecules escaping is much greater than the number of molecules re-entering the liquid. As time progresses, the number of molecules escaping slows down, and the number of molecules re-entering the liquid increases, but eventually also begins to slow down. Eventually, for every molecule that escapes, another molecule re-enters the liquid. This is a state of dynamic equilibrium, where the total number of molecules in the atmosphere stays constant. The equilibrated vapor above the liquid generates a pressure inside the flask. This pressure will depend on the identity of the liquid and the temperature. This pressure is the vapor pressure of the liquid. All liquids have a vapor pressure. Some liquids have a much higher vapor pressure, meaning that the number of molecules in the atmosphere above the liquid is very large. A liquid such as gasoline has a high vapor pressure. Liquids with high vapor pressures are called volatile liquids. Low vapor pressure liquids are called non-volatile. The more volatile a liquid, the weaker the intermolecular forces. The weaker forces make it easier for the liquid molecules to escape and generate a high vapor pressure. As our final example, we were going to order the following compounds from highest to lowest vapor pressure. The compounds are CH2Br2, CH2Cl2, and CH2I2. Even though each of these molecules are polar, it turns out that the dispersion forces are the most dominant forces. Recall that dispersion forces are determined by the size of the atoms in the molecule. And since we want the highest to lowest vapor pressure, we want to begin with the molecule that has the weakest intermolecular forces. Since chlorine is the smallest of the three halogens included here, we would expect CH2Cl2 to have the weakest intermolecular forces. CH2Br2 should have the next strongest forces, and CH2I2 should have the strongest intermolecular forces. And from this, we see that CH2Cl2 should have the highest vapor pressure, CH2Br2 should have the middle vapor pressure, and CH2I2 should have the lowest vapor pressure. This is verified when we consider the experimental vapor pressures for the three molecules. CH2Cl2 has a vapor pressure of 46.5 kilopascals. CH2Br2 has a vapor pressure of 4.59 kilopascals. And CH2I2 has a vapor pressure of 0.113 kilopascals. Lastly, we will consider the effect of temperature on vapor pressure. The plot to the right shows the temperature dependence of vapor pressure for several compounds. Notice that the vapor pressure increases exponentially as the temperature increases. A second feature of this plot is that the compounds with stronger intermolecular forces have curves that lie at higher temperature, or farther to the right, than compounds with weaker intermolecular forces. Diethyl ether is the compound with a vapor pressure curve that lies to the leftmost. It is a very small molecule which only has dipole-dipole interactions. On the other hand, water and ethylene glycol, which are the two curves on the right, both experience hydrogen bonding. Lastly, at any temperature above where the vapor pressure crosses the dashed line, a compound will no longer exist as a liquid at normal pressure. Rather, it will exist as a gas. From this, we see that above 100 degrees Celsius, 4 of the 5 compounds will exist as vapors rather than liquid, and only ethylene glycol will still be a liquid at those temperatures. In closing, let's review the relationship between the strength of intermolecular forces and the properties we have discussed. As the strength of intermolecular forces increase, the density will increase. As the strength of intermolecular forces increases, the viscosity will increase. As the strength of intermolecular forces increases, the surface tension will also increase. And lastly, as the strength of intermolecular forces increase, the vapor pressure will decrease.